So what are near-Earth objects? So near-Earth objects are essentially asteroids or comets which can come very close to the Earth, that is in opposition to main belt asteroids. So and they are leftovers from the inner solar system formation process. And astronomical surveys have been very successful at discovering asteroids, and the sooner they're found, the better. So essentially the name of the game is find them before they find us, right? And then even so, there are still some issues because we have some observational bias towards the outer parts of the solar system, so we should map better the inner parts of the solar system to get a better situational awareness of how all the near-Earth asteroids population is composed. So what I'm showing there is an animation from the NEOs data. So what you see in gray is just main belt asteroids discovered by that mission, and the dots in green are near-Earth asteroids. So those are the asteroids that are either completely into the Earth's orbit, or they can also cross the Earth's orbit that eventually can impact it. Okay, so we have here, if we had a perfect knowledge of an orbit state at a given time, then we could predict with perfection how they are going to behave in the future, and either predict if they are going to impact the Earth or not. But in reality, we have uncertainties from observational models, and also from force parameters that come into the dynamical models, right? So we have to be very careful when propagating these orbits, and also the orbital uncertainties. So that's where our package enters, right? So we developed this basing on Taylor integration, which allows very high accuracy orbital propagation, and also allows us to do simultaneously two Taylor series expansions, and we call that jet transport. So we use one Taylor expansion to propagate in time, and we use the second Taylor expansion to keep track of small variations with respect to the initial conditions. And we are able to perform orbit determination using optical and radar astrometry. And also we are able now to do preliminary orbit determination using Gauss method. And so what is jet transport? Jet transport is what I was telling before. It's a way to keep track of, for example, if we have a nominal or reference initial condition, say x0, and we have small perturbations to that reference initial condition, then we can keep track of it as in terms of a truncated polynomial algebra. So we treat this perturbed initial condition as a vector of Taylor ends of float 64 in Taylor series in Julia. And that allows us to keep track of how this neighborhood around the reference initial condition deforms in time. Okay, so what I want to say here is just that using several packages from throughout the Julia ecosystem of packages, we have been able to ingest into our NEOs.jl all the information that we need and do all the statistical treatments that we have to do on optical astrometry, for example, and also do all these transformations between the different frames that we can define with respect to the Earth. And for that, we use in particular satellite toolbox transformations. And then, for example, for our optimization procedure, that is finding the minimum that we can find in the mean square residual function, which is our loss function, we can essentially treat our loss function as a Taylor polynomial in the perturbations of the reference orbit, and then we can minimize that, and then it's very straightforward to find the best candidate, right? And then in particular, I want to talk about asteroid Apophis. So it was discovered in 2004. It has a diameter of about 400 meters. And just 2 days after being discovered in June 2004, it was lost, and it was recovered until December 2004. And around the late December 2004, the impact probability for the date on Friday, April 13th, 2029, reached a maximum of 3%. So that's a record to this date, and to this date, Apophis is said to be the poster child of near-Earth objects, just because it surprised the astronomical community when it was discovered, right? So just to show you how the situation was, we prepared this little widget. So what you're seeing here is the target plane for the impact in 2029. So the black circle is just the Earth's cross-section in this plane. And if the actual orbit of the asteroid goes into this circle, then we have an impact, right? And we have what we see in in green is the uncertainty region. So what we had in the beginning, in around early December 2004, was just this a huge uncertainty region, right? Which we couldn't say that an impact in 2029 was impossible. But as we got more and more and more observations, then that's how we discarded an impact in 2029. But the problem is that even though we discarded the impact for 2029, there was still a possibility of impact in, for example, 2036 and 2068, which are represented by these by these arcs, the circles, the purple and the blue circles. So for example, if the actual orbit in 2029 should pass, for example, around this area, then we would have an impact in 2036 and the same for 2068, right? But then what we did was precisely, okay, so that's just a video of the same thing that I was telling you guys. So what we did was take even more data up to from 2004 up to 2021. And so this is the actual situation that we will have in 2029. So we won't have an impact, but it will come pretty close. Actually, it will come, it will intersect some satellites' orbit. So yeah, it's a near miss just by very little. And indeed, yeah, the question remained open up until very recently of whether we would have an impact later on, right? So, for example, what we did with our orbital fit to Apophis was that if we take into account only gravitational effects, then we cannot fit all the orbital astrometry, all the optical astrometry. But if we take into account also non-gravitational effects, such as the Yarkovsky effect, which is similar to solar radiation pressure, right? It's a radiative effect. And if we take that into account, then we can indeed fit all the optical astrometry. And we have the residuals behaving as a Gaussian. So yeah, we don't have any systematics going on in there. And then, for example, to fit the radar astrometry, that's very, very difficult to make because we have very high fractional precisions. And for example, a nice application of automatic differentiation that our package allows is just that, for example, if we know that the time delays from radar and the Doppler shifts are related by this differential relation. And using our 80 setup, then we can compute the Doppler shifts just straightforward, and we don't need any special things around going on. And then what we found here as well is that using only gravitational effects, we cannot fit all the astrometry. But if we take into account the Yarkovsky effect, then we can indeed fit all the data, both optical and radar. Okay, so what about the impact for later dates after 2029? So what we see here is the orbital uncertainty distribution plotted with respect to a variable which we call zeta, but it's essentially the orbital uncertainty distribution. And what we knew before 2021 was just this, the blue distribution. And after incorporating observational data up to 2021, Then we obtain the orange distribution, and then these lines, which represent the little arcs that I was showing before for a possibility of impact in 2036 and 2068, which are called the gravitational keyholes. We see that after incorporating astrometry from up until 2021, then these later impacts become impossible. And a full impact assessment of Apophis done by JPL, for example, shows that we know that Apophis won't impact the Earth in 200 years at least. After that, we don't know, but we are going to need more data for that. Okay, so now about the preliminary orbit determination, I will leave the floor to Luis Eduardo.
Okay, so Apophis was kind of the motivating example to develop this package, but now we have two main objectives for the future. The first is what's called preliminary orbit determination, and that's being able to get an orbit directly from the observations. The most common way to do that is via Gauss method. That was developed by Gauss in the early 1800s to determine the orbit of Ceres. The method basically takes as input 3 optical observations and returns a preliminary orbit. The optical astrometry only gives us information about the angular position of an object in the sky, but we have no information about the distance. So pretty much the core of the Gauss method is deriving analytical formulas for the coefficients of an 8-degree polynomial whose solutions are the possible distances between the sun and the object. It's important that even though it's an 8-degree polynomial, it only has 4 terms. And it turns out that the polynomial can have at most 3 real positive solutions. And that's important because when we encounter multiple solutions, we have to check them all to check which one has the best fit to the data. Also, in order to give analytical formulas, Gauss method does a series of approximations that are often not good enough. So the method is often followed by a refinement step. Also, in our case, we leverage from the Taylor series.jl package, and we treat observations as jet transport variables. That means basically that instead of using floats, we use a float plus a perturbation. And we can use Taylor series to do the same process, but with jet transport perturbations. And that will give us a polynomial that depends on the perturbations, which we can propagate in time and use Newton's method to fit that polynomial to the observations that we have in that moment. The other objective that we have is automating the orbit determination process. That's basically because nowadays there are hundreds of observatories reporting new observations every day of new objects, of past objects, etc. So we would like to have a script running and analyzing all those observations. And so far we have a small script that kind of goes in that direction. We did a small run here. And basically it starts printing out some parameters. But here we applied this script to asteroid 2023 DW. This was discovered in late February of this year, just a couple of months ago. And we only have 123 observations, which is very low compared to over 9,000 observations that we have of Apophis. So the script starts by downloading all the observations available from the Minor Planet Center, which is the organization that reports all this data. Then it continues with Gauss method. In this case, you can see kind of 3 batches, and that's because this is one of those cases where Gauss method gives 3 possible solutions. So it has to check them all to see which one is the best. And here it gets to a successful set of initial conditions. After that, it can do a full integration to cover all the 123 observations and use Newton's method to fit a final orbit to the asteroid. This Q that you can see here is basically the function that we're trying to minimize in Newton's method, and well, just saves the results. So far, this script, we can specify which NEO we want to analyze, and we can do the whole process, but there's still a lot to do with this script to make it fully automatic. And finally, two interesting things. The first is that asteroid 2023 DW would get very close to Earth on Valentine's Day in 2046, as you can see in these results. The plot on the right represents the geocentric range, that is the distance between the Earth and the asteroid over this century, and the lower half is assumed to year 2046 when the close approach is going to happen. Now, when we do Newton's method, we need a weights scheme, and that's basically to assign an orbit and observational uncertainty to each measurement. However, currently the Minor Planet Center do not give any information about the uncertainty of each observation. So we implemented a scheme published by Benet in 2017. But also other organizations like NEOs, which is based in Pisa, have other weighting schemes. And as you can see here, the different weights can give very different uncertainties, especially in a case like this with very few observations. In the last row, we have the JPL reported values for comparison. So finally, as we said, kind of the motivating example that led us to develop these packages was to determine Jarkovsky effect for Apophis and use that to rule out possible collisions in future years. Also, we've implemented Gauss's method for initial orbit determination, and we plan to implement more methods. We're interested especially in those that are specially designed for cases with very few observations or observations that are very close in time, cases where Gauss's method tends to do pretty bad. Also, by treating pretty much everything as a Taylor polynomial, we can easily do high order AD. We also have we also have a data frames extension that turns out to be really useful to filter observations, and that will be useful in the future for outlier rejection, among other things. There's still a lot of performance we can gain, especially when it comes down to cutting down allocations, because Taylor method can be quite precise, but also allocates a lot of memory. And we also have to deploy a full documentation. And among other things that we can implement are a square root information filter, systematic ranging, which is another method for initial orbit determination, to improve our dynamical models and also automate the impact assessments. So that's all. Thank you.
Yeah, that's the line of sight of. Yeah, the question is, what is the white line? Yeah, that's the line of sight. The newly discovered at that point in time. The newly discovered objects at the point in time. Yeah. Yeah, exactly. Yep. Yeah. So the question is why we picked Julia. Essentially, you could say. Yeah. So we found many advantages of using Julia. So for one part, these high-order automatic differentiation schemes are very easy to implement and to treat in Julia. Like the language lends itself pretty easily to these kinds of schemes, and also all the, we didn't show all the details, but incorporating all the data sources, either, from NASA, from all the international astronomical union parts, the Minor Planet Center, like all the different data sources, we have been able to incorporate them very well using all these different things that we can use in Julia, for example, artifacts, or for example, Scratch.jl allows us to assimilate very different kinds of data, which that we found, right? And yeah, so there are many things and many advantages to using Julia to do this kind of analysis. Yeah, please go ahead. Yeah. Yeah, so the question is whether these kind of techniques could be useful for Earth satellites, and the answer is yes. The only thing that you would need for that is implementing a high order orbit propagator for Earth. Because, for example, right now we only use the some of the lowest order zonal harmonics of the Earth, right? But to have a high precision orbit propagator, you would need all taking into account all the higher order, zonal tesseract harmonics of the Earth, and yeah, even perhaps variations with time, etc. So that's the only thing that you need. But yeah, other than that, I mean, you can open always a pull request in NEOs.jl, and we could get that implemented. Yeah, for sure. It's the question is, what's the size of Apophis? It's about 400 meters. So for the curious mind, it could destroy, for example, a mid-size city. So it's not. The question the question is whether we can blow it up before it comes here. Well, it would be there's the Icarus project, which actually run here at MIT in the 1960s. So that would be one possibility, but there are actually some other, you could say, smarter and perhaps cheaper options, which are actually being tested right now. For example, there was the DART mission from NASA, which is going to be also going hand in hand with the Hera mission, which we are going to operate at ESA. And for example, these missions, what they are trying to do is perturb the orbit of an asteroid. The sooner you can perturb the orbit, the better, so that you make the post-impact orbit be a miss rather than a hit. So yeah, but I mean, yeah, for if you were to find an asteroid with just like not seconds, okay, but maybe days of before arrival, then perhaps the options could be more nuclear, yeah. But that's precisely why it is so important to find them as soon as possible. So, yeah.